Sure,
like,
it has
what?
he does like flying.
Yeah.
And then he uses L'Hopital's.
Wow. And one of those houses.
Okay, since my permission, I like to say a couple of words about the homeworks. For this assignment, in fact, probably pretty much for anything, you can assume that if I say ring, I'm confused with identity, unless I tell you otherwise. And number one, we say the R module M is simple if its only submodules are itself and zero, right? Show that if M is simple and phi from M to M is an R module homomorphism, then phi is either 1-to-1 or it's the zero. So only one of those two things, which is kind of cool. Q is a Z module, right? Remember last time, any abelian group is a Z module in that way that we defined. It is impossible to put a Q module structure. So if your ring is Q on Z, it's impossible. We'll see a reason for this later because it turns out any Q module, any unitary Q module, is a vector space, right? And that has to be some number of copies of Q, so this is impossible. But get your hands down and dirty with this one, and you do this little computation. It's impossible for Q, a unitary Q module structure on Z. Of course, let me point out that if you have any ring, so this is a follow-up to one of the things you asked last time, John, is if I have any ring and I have any abelian group, I can put an R module structure on an abelian group just by declaring that R times A is 0 for every A in there, right? That is the stupid module structure, right? But it's not unitary, right? Because 1 times something has to be 0, right? And in fact, I don't want to already get you hated by all of your peers, but I've got a generalization of an answer to your question that will be one of the questions on the next homework. But it's a fun little problem. It really kind of is. I'm going to explain to you what this is later. This is the set of all R module homomorphisms from R to M. So notice any ring is itself an R module just by taking the multiplication from the ring. So this is kind of an easy R module R. The set of homomorphisms actually is an R module. We'll talk about that later. Hom Rm is actually isomorphic to the module M. So you can think of sort of canceling the R's out in a certain sense. Number 4, one of these is easy if you use your eyeballs and look at part 3, right? Compute the following: hom Z, Z homomorphisms from Z to Z mod N, and the Z homomorphisms from Z mod N Z to Z. Compute both of these. This I don't think will take you very long. Number 5, we say the R module M is cyclic if there is an M and M such that M is R times M. So if the module is sort of generated over R by a single element. So everything in M is just some R times this fixed little M. Show that if M is cyclic and phi from M to N is an R module homomorphism, then phi is completely determined by phi of M. That is to say, this is sort of like what you got in linear algebra. Remember, do you remember back in 3110 or wherever you had it, if you had a basis for a vector space, if you know where the linear transformation takes each basis element, you know the linear transformation. It's the same idea here, right? If you know, if it's a cyclic module generated by one thing and you know where M goes, the generator, you completely understand the homomorphism. Show that the homomorphic image of a cyclic module is again cyclic. And the last one, is it true that a submodule of a cyclic module is necessarily cyclic? Prove this or give a count. Okay, that should be a fun one to start things off. Any questions? There we go. Okay. All right, so the last thing we were talking about is we talked about the direct sum of R. Well, R is with 1. This is an R module. Given the R action, R times the sequence So if the index set is finite, then you might just consider this like, say, an n tuple, and you just slide the R through, just like you did with a scalar multiplication. In linear algebra, now, I'm going to go into, we need to talk a little bit about morphisms. Once again, you got to love algebra, right? You go through groups, you go through rings, all this business, and it's always kind of the same idea, right? You have a structure, and then you have the appropriate homomorphism notion for the structure. So, definition, let's suppose A and B are R modules. You could do this with left, but I'm just going to abandon that. Definition. Again, my disclaimer is you can do this much more general, but I'm really not caring here. And A, B are modules. So we've got two R modules. Let's suppose we have a function we say F is an R module homomorphism Of course, this is a definition, so we can do anything we want, but what do you think is a sagacious thing? I mean, we're talking about modules here, and we want to have this homomorphism respect the module. So how do we do that? Well, what is a module? It's an abelian group. So this thing better be respecting the abelian group. So we want that f of x plus y is f of x plus f of y for all x, y in A. Step one just says, hey, a module is first and foremost an abelian group, so I'm going to have this be an abelian group homomorphism. It respects the additive structure. What else do modules got going on? They got that pesky scalar multiplication. We want our homomorphism to respect that. So what do you suppose we should do here? Right, I mean, you might be tempted to say f of r, f of x, but that wouldn't make any sense, right? Because r is not in the domain of this. So the best thing I can do is slide that sucker out. Notice that this is exactly the definition you probably saw in linear algebra for a linear transformation. That's exactly what this is, couched in terms of modules. If, in fact, R is a division ring, now let me remind you, a division ring is a ring where every non-zero element has an inverse. To use this in all generality, I should have said like left R module or whatever, but the definition is the same. If you restrict to commutative ring of one, a division ring is a field, right? Then F is called a linear transformation. So there is a notion of linear transformation and vector space over a division ring that's not a field, but we're not going to dive too deeply into that. Any questions? So I think that's what you want it to be, right? This is what we would want an R module homomorphism to be. Let us give the following lemma. Lemma 6. Let us suppose that we have phi, well, suppose them in R modules. And we'll let phi be a function from n to n. Then phi is an R module homomorphism. Squeaky's marker in the free world. Phi is an R module homomorphism if, well, actually, if and only if phi of x plus ry is phi of x plus r phi of y for all x, y in M and R in R. So in other words, this is a one-step stop to testing for R module homomorphism. You don't have to separately check this. You can just check this one thing. Let's just forget we'll prove this. Yes.
For like the definition, why does R have to be an element of B, but then
It's not, I'm sorry, that is a very, almost needs to go to the hospital R.
Oh, okay.
That's the B, sorry about that. Yeah, that's a good question, because if it was in B, there would seriously be problems with that. Okay, let's assume first that phi is an R module homomorphism, and we wanna do this, all right? So I want to show, well, look at this right here. This is I can break it up here because of my first assumption here, all right? So now that I've gotten down, and I only have to do my sucking the R out on the second piece. Oops, and there we go. No problem there, right? The interesting way, the interesting part is why do you get both of these from just this one, right? So let's see what's going on there. Okay, so we have clear, we have for all x, y in M and R in R, phi of x plus ry is phi of x plus r phi of y. I can always do that big fell swoop thing. Okay, so I'm gonna put this here star. For number one, that is to show that this works. Take R equal 1, right? Convenient, right? Because this turns into 1, and so you have phi of x plus y is phi of x plus 1 times phi of y. Everybody okay with that? And for 2, I guess what I can do is take x equals 0. And if x equals 0, that gives phi of ry, and phi of x is 0, right? Because well, I guess I need to prove that, don't I? So let me not stop here. Let's take x equals 0, and we get phi Ry is phi of x plus r phi of y. Right? So I agree with that. So it suffices it suffices to show that phi of x equals 0 given what we have. Any ideas on how to do that?
It's a homomorphism, so shouldn't it take 0 and 0?
Right, but we're only assuming this. Right.
Oh, right.
Do we show?
No.
Yeah, no, actually, his remark is correct, because actually. This is true, because. B is an abelian group homomorphism by previous step. So you save me from reinventing width, right? When you take R equals 1, we prove property 1, that phi of x plus y is phi of x plus. So that means it's an abelian group homomorphism, and therefore phi of x has to be 0. Or, well, I'm sorry, phi of 0 has to be 0. Good questions on that. Okay.
So the only difference, like making it our module homomorphism is the scalar or like the.
That's right. That's right. And so let me add to your comment as follows. So if your ring is Z in my definition, so if it's Z module homomorphism, it's the same as an abelian group homomorphism, because now your R is just an integer, right? And so it reverts back to the ordinary abelian group homomorphism. So that's a good observation. Here's another one. Here's some examples, R module homomorphisms. Fn. Let's let you. Consider F in Z scale. F in M is N times N. Notice that X, Y, B, and Z, and R, B, and Z. So I kind of distinguish a bit. Here's the module, and here's the ring. F in X plus Y. Oh, I'm sorry, X plus RY. Well, by definition, that's just taking this whole kit and caboodle here and multiplying it by N. And this is NX plus R in Y. Because of course the order doesn't matter in RN. And this is N times, this is F sub N of X, and this is R times F sub N. So this homomorphism is just multiplication by the scalar, just uniform multiplication by n. This is an R module homomorphism. It is not a ring homomorphism unless, anybody give me a condition on n for which this is a ring homomorphism? Can you identify an n that makes this work? Oh, Megan, let me talk to you after class too. Notice that yeah, so it's got nothing to do with that. I just popped back into my mind. Notice if n equals 1, this is just the identity function, right? And that's a ring homomorphism. One could argue that n equals 0 might work too, because that's just the 0 map, but it depends on whether you want your ring homomorphism to take 1 to the identity or not. Okay, here's another good one here. This is kind of another similar example of this, only it's on sort of a larger scale. Or be print 1 and let m equal x. So if you don't remember this notation, this was a ring that you probably studied in 4120. It's just polynomials with coefficients in R. But here I'm treating it as a module. I'm not worried about multiplying polynomials. I'm just adding them and I'm multiplying them by elements of the ring. So in other words, if you had R times this polynomial, okay, xk, this is RA0 plus RA1x, RAKXK. So that's the way that module structure works. The function G from Rx to Rx given by G of f of x is x f of x is an R module homomorphism. This is of the spirit of this one, where you're just multiplying one thing. But see, the difference here is you can actually multiply something out of the module, right? So that's what we're doing here. So you take any polynomial, and you multiply it by x. This is actually an R module homomorphism. You should check that is true. It's not too difficult. With the R module homomorphisms, I might add any of the familiar kind of modifiers, like an R module epimorphism, an R module isomorphism, R module monomorphism, for example.
These aren't automorphisms though, right?
Well, an automorphism, again, you could use the automorphism, but that would have to be an R module homomorphism from the module to itself that is both one-to-one and onto. Okay. Proposition. Here's another one, which you saw me sort of bring up in your homework. Oh, and by the way, I just wanted to remind you, if you haven't done it already, which I think most of you have, there is a homework due today. It's that silly thing about, your history kind of thing, but be sure and do that. Let M and N be R modules. And here I'm gonna start off with just a ring one. I'm not gonna mess with any of this stuff that's not unitary. The set. Home R M N. Home, you hear that turn off, home is like homomorphism. Right? This is the set of phi from M to N, such that phi is an R module. Homomorphism. So just consider that set as it is. This set can be made into an abelian group. Under pointwise addition. And of course, pointwise addition, that's just the way you're used to adding functions in calculus. So what I mean by that is if f and g are in home or in n's, they're functions from n to n, then f plus g of m is f of m plus g of m. And this makes sense. Pointwise means, what does it mean to evaluate f plus g at m? It's just evaluate f at m and evaluate g at m and add them up. And it makes sense to add them up because both of these animals are in the module n, so I can add them up. Right? So under this is an abelian group. Of course, the zero operation is the zero function. It's the one that takes everything in m to the zero and n. The minus, the minus of f of m is the one that takes, the minus sign of this just takes everything to the opposite of whatever f does. So it takes it to minus f of m, and so forth. And so this is an abelian group. There you go. It's an abelian group. If R is commutative, then it's an R module. And this is what we will focus on. Home R M N is an R module. Now I'm digging on this because this gives us a way to build another R module from existing ones. Goodness gracious, if it's an R module, I better tell you how the multiplication works. Right? So how do we do this? We and let R be an R. We define I need to define, so if I've got some homomorphism from n to n, and I've got some scalar, what does it need to be a scalar times the function? Well, I want to define this by telling you how it works. How does my new animal, R phi, act on M? What's the easiest thing to do? Just multiply R by phi of M, right? Right, okay, well. So I think it's sort of the most natural thing you might think to try. Yes, I know he's going to ask a question about commutative.
No, I was gonna ask about, is this hom R, this is basically, like two steps generalized of like GLN, right? Like the general,
Oh, well, so when you're talking about GLN, what you're talking about is you're talking about,
Well, it's not.
what's it now?
No,
Well, you're talking about a group, but you're also, I mean, you're looking at, you can think of, well, see, the problem is GLN, you,
no, it's an R module.
uh, in what sense? Because GLN first has to be a Boolean group. So if you're gonna let it be in a Boolean group, you're gonna have to add the matrices up, and now you're no longer gonna necessarily have to term it as zero.
Oh, okay.
Right, that's the problem here. But you can think of it, I mean, this kind of thing does come into play here.
Oh, so it's just the matrices of size and.
Right, so, okay, there's gonna be actually a connection for free modules. In general, it's a little bit more Wild West. But I think the connection you're trying to make, correct me if I'm wrong, is, okay, so you've got these linear transformations. At least if the vector space is finite dimensional, then you can start talking about n-by-n matrices, right? Yes, there will be some things that you can do sometimes with certain types of modules here, but in general, this can be a pretty abstract stuff, right? Now, let me answer the question that I thought he was going to ask. Why commutative, right? Pointwise addition, this is always a Boolean group, come hell or high water, right? Why do we need commutative here? Well, let now, one of the things that we need is you need RS phi for this to be an R module. Right? This is like one of the big things we need. You need RS acting on phi to be the same thing as R acting on S phi, right? Everybody okay with that? Now, notice here, let's break this down basic. If this is a linear, if this is a homomorphism, just think of this blob as a single capital phi, right? I should be able to factor that R in, right? So this should be because this whole blob is an R module homomorphism. Everybody agree? So I have to be able to pull that R inside there, right? And of course, now I can go back to basics and say, well, but phi is an R module homomorphism as well, so I should be able to pull that in, right? So this is phi. Everybody agree? But if you look at this, RS is a single element in R. I should be able to pull that whole chunk in there. Now look at, compare these two. I'm not at all convinced that this is well defined unless I can assure myself that the ring is commutative, right? If it's not commutative, this potentially could go wrong. Okay, any questions on that? Okay, more definitions. Okay, so we've talked about the homomorphisms. Another thing that we look for is substructures, right? We looked at this in groups and rings, so subrings, ideals, subgroups, normal subgroups, things like this. Yeah, I'm not. Definition. Well, in. Let M be an R module. And in M a subgroup. Now, of course, what I'm going for here is I'm looking to define what a submodule of module M is. Well, better be a subgroup, so I've got that taken care of. What does it mean to be a submodule? Well, it means it's vacuum cleaner, very much like an ideal. We say in M is a submodule. Well, let me see, R submodule of M if R times N is contained in N for all R in R. Or equivalently, Rn is in N for all R in R, N. So it's very much like an ideal, right? I mean, it's an ideal, it's sort of like doctrines without borders. It's ideals without having to be inside the ring in a certain sense. It sucks it in. That's what it means to be so in other words, another way to think of it is it is a baby module inside the parent module. Okay. This result probably looked familiar because when we talked about groups, when we talked about ideals, you probably had a similar theorem of this ilk. Proposition 12, 111. Let N be an R module, let N be a subset of N. Then N in M is a submodule of M if and only if N is not empty and for all X, Y in N, R in R, X plus RY is in N. This is similar to, I guess it was called subgroup criteria, and it's like the kind of one-line thing for ideals as well. And I am going to go through this because, you know, why the heck not? Let's go over proof of that, but first, any questions? Okay. This way, I think is the easier way, perhaps. Suppose N is a submodule of M. By definition, N is not empty, right? Because any submodule has to contain at least the zero. What else? We need to show for all x, y, and n, r and r, x plus r, y is an n. Well, suppose x, y is an n and r is an r. Then ry is an n because it's a submodule. Therefore, x plus ry is an n. And there you go. That's all we need there. How about the other side of the coin? This one's always the more interesting one. Why is it why is it this gets to be a one-stop shop? You only need to check one thing. Suppose n is not empty and all x, y, and n are an r. X plus ry is an n. Well, we need to show that n is a submodule. Well, first, since n is not empty, there exists x and n. Actually, it's really kind of silly, but logically, I do need this. Right? Since it's not empty, there's some x and n. Now take x equal y and r equal to -1, and we get oh, yeah, I don't need anything. Yeah. So take x, y, and n. So just pick any two elements out of n. We know that there's at least one in there, and I'm not demanding that x, y even be distinct, right? Just take two random elements of n and choose r equals negative. That's what. Then x plus -1y is an n. So because that's the subgroup criteria. So now I've picked r as -1. So now that I know if x and y are in there, then x minus y is in there. So this is indeed a subgroup. So I've got half my battle fought. Now I've got to do is show that it's a vacuum cleaner. So let's let y be an n and r be an r. Choose choose x equals 0, and we have 0 plus ry, which is ry, is in n. So n in n is a submodule. Fantastic. Okay, any questions on that? Okay, here's sort of another example that is also, I'm going to define stuff in the example as well, but this is stuff you've seen before in a different context. Example 12.1.13. R being rank 1 at f from A to B and R module homomorphism. The kernel of F, which is all the stuff in A, such that F of A equals 0, is an R submodule of A. By the way, you saw this business in 3110.2, in the context where your module is a vector space and the kernel of F is the null space of the linear transformation. That's what this is in more general setting. The image of F, this is all the stuff, well, it's just the set theoretic image of A. Is an R submodule of B. And I'm going to generalize the kernel a little bit. Also, if C is a subset of B, not empty, then F inverse C, which is all the crap in A, such that F of A lives in C, is an R submodule of A. By the way, can somebody point out to me, why is this a generalization of kernel?
Because C is equal to 0.
Right, the kernel is F inverse of 0. I agree with that. So let me prove. So let me prove the statement of this. All these subsets are subgroups of appropriate A, or whichever is a subgroup. These are all subgroups. This is, I hope you saw this in 4120 at some point, right? That all these structures are subgroups. The kernel of F is a subgroup of A, the image of F is a subgroup of B, and so forth. And that preempts thing too. So we will prove, I will leave the image as an exercise. It's not too hard. And I will prove this because ding, ding, ding. I like proving this because it proves that one too. Right? So we show F inverse C in A is a submodule with the emphasis on module because I already know it's a subgroup. Okay, well, let R be an R and X in F inverse C. Well, what does this mean? Since X is in F inverse C, then F of X equals C and C. By definition, that's what that means. And therefore, RC, which is a refreshing color, but also here RC is R times F of X, which is F of RX, which is in C. Yes.
How do we know that F inverse C is non-empty?
Because it has F0 in it. because 0 goes inside any module, right? Because over here in B, over here in B, F inverse C, notice 0 goes to 0,
Right.
because it's not a model homomorphism,
Right.
and 0 is in any submodule of it. So
So
out
is
here,
C a submodule or just a subset?
yes.
Okay.
Yeah, this doesn't hold C, it's not a submodule.
Okay.
Doesn't make sense, yeah, I should have, yeah, and I wrote not empty because apparently I wanted to confuse you. But anyway, so R times C is in C.
Okay.
Right? So F of R X is in C, therefore Rx is in F inverse C. And so F inverse C is an R submodule of A. Okay. Any questions on? This is the appropriate place to end. Don't forget your sort of pseudo homework for today. I hope you all have a great weekend. Pick things up for the math club, which will start next week. And yeah, have a good weekend.